Hey class. So what we're going to look at now is Fischer projections of sugars. So if we look over here on the left, the way you want to draw Fischer projections is you're going to take the most oxidized carbon. All right, so don't forget that this one up here is the shorthand for an aldehyde. So let me just draw it out for you real quick. It would look something like this, where we have a double bond to an oxygen and then the rest of the carbons coming down. All right, the reason I want to draw that out is there's two oxygen bonds to the carbon, right? It's a double bond, so there's two. That makes this the most oxidized carbon. So we also want to put the most oxidized carbon on top. All right, so let me just put a note of that. Most oxidized, and I'm just going to put OX for oxidized. OX goes on top, and then what we're going to do is put the carbon backbone right down the middle. So we're going to take the carbon backbone and put it right down the middle. And then the two groups that come off of the carbon are just going to be on either side. So for sugars, it tends to be hydrogen, oxygen, the same. So we'll have our alcohol group, right? The oxygen OH makes an alcohol. And so on both of these, it's just oxygen, hydrogen, oxygen, hydrogen, oxygen, hydrogen. And then the side they go depends on the stereochemistry. And so we'll get into that in a little bit. All right. So the really nice thing about this is we don't have to draw dashed and wedges. And the reason for that is that the assumption we're going to make in Fischer projections is that any of the groups coming out to the right or left are going to be wedged. All right, so if you come over and look at the picture just to the right, all the groups on the side have wedges, all right, on both sides. And it's not shown here, but conversely, what you can think about is these lines would essentially be dashed, so it'd be kind of going away from you. All right, so we still have that tetrahedral shape. All right, and the best way I've thought about to memorize this is, I know it's going to sound cheesy, a little nerdy, but your molecule loves you. And so you can think of these as arms coming out to hug you. All right, so the hydrogen and OH are going to come out and hug you. And so that's how we know they're always coming towards us, right? So the ones on the side are always wedged. All right, the other thing we can do is everywhere you see a crosshair, right? Over here on the right, we've actually drawn out the carbon, right? And we've done the same here. So as we're looking at these carbons, if you notice, over on the left, we actually didn't draw those out. And the really nice thing about this is what it's trying to do is highlight that these are chiral centers. So each of these that have a green dot, when we don't draw out the carbon in a Fischer projection, all right, only a Fischer projection, remember zigzag, we don't draw the carbons either. But in a Fischer projection, when we don't draw the carbons, what we're actually telling you is that these are chiral centers. So this one actually has 1, 2, 3, 4 chiral centers. And it's a really easy way to highlight that we have chiral centers. And so if we kind of went through this, we could look at each one of these and realize, okay, this carbon's attached to 4 different groups. And even though these are both carbons, there's some difference in them. And then the hydrogen and oxygen are clearly different. So the nice thing about the Fischer projection is it gives us those chiral centers in a really easy way to see without us having to solve for, are there 4 different groups and ranking them in priority, things like that. All right, the last thing I want to highlight is when we look at a sugar, a lot of times what we're trying to find out is it an L or D sugar. Okay? And what we want to do is look at this last group here on the bottom. Right? And so what we're going to do is see if the highest priority, right? So in this case, what we're comparing is the oxygen, right, from the OH and the hydrogen. If the highest priority is on the left, it's going to be an L. If it's on the right, it's a D. In this case, the OH is on the right, so it makes it a D. All right. So in other words, for this to be an L, the OH would have to be here. All right. So we want to look at the chiral center farthest away from the most oxidized. So it's the very bottom chiral center, right? So it's the last chiral center on the bottom, and look at what side the OH is. If it's on the right, it's going to be D. If it's on the left, it's going to be L. So let's just write that. So if it's on the left, it's L. It's D if it's on the right. Okay? And what we're talking about is that highest priority down here on the bottom. All right, so that OH. All right, so let's try this together. So I've got 3 molecules for you. So why don't you pause the video and try to solve for each of these. So tell me how many chiral centers there are, and then whether it's L or D. All right, so hopefully you had a chance to look at this. On the first one, if you notice, there's only 2 crosshairs, so those are my chiral centers. So this one has 1, 2, so there's 2 chiral centers. All right, so let's write that. All right, if we go to the next one, 1, 2, 3, and I'm just going to put 3 up here because I think we know that we're talking about chiral centers. And then we can do the same with the last one, 1, 2, 3, 4. And so there's 4 chiral centers on the last one. All right, the other thing I wanted you to do is tell me if something was L or D. And so what we want to look at is the one farthest down. So we're going to take our most oxidized at the top, and we're going to find the last chiral center we identified. So in this case, it's this one. And now what we want to look at is, where is that highest priority? In this case, it's the OH. And since it's on the left, since the OH is on the left, it makes it an L. I'll just write left below it. So this is going to be an L sugar. All right. We can do the same thing on the next one. In this case, the OH is on the right. Remember, it's always the farthest one down. All right, so the farthest one away. And now in this case, it's on the right. So hopefully all of you got that this was a D sugar, okay, because it was on the right. And then the same for the last one. We find the one farthest down to the bottom. It's on the left. So that makes it an L. All right, so it's an L sugar. All right, so hopefully a couple things from this. The Fischer projections are an easy way to kind of see sugars. Okay. It lets us identify whether they're L or D pretty quickly, right? If you think about the time we spent doing R and S, it's a little bit more challenging. The way we draw this highlights that group on the bottom, whether it's an OH or we'll see this for amino acids with an amine. And just look, if it's on the left, it's L. If it's on the right, it's D. All right, so the key is you got to get into this Fischer projection, right? Most oxidized on top, carbon's right down the middle, and then the OH is going either side depending on the stereochemistry. All right, so it's kind of a nice way to represent the molecule. All right, I hope this was helpful.